it's a great pleasure and honor to be able to talk to you this afternoon and tell you a little bit about things I've been doing for the last 30 years. I won't go into all the details of all the PT paths that we've looked at, but it gives me a chance to look back at where this all started and then to tell you where we are today and what we're going to be trying to do in the future. I have one comment about the previous talk, though. From my perspective, ice really isn't a sediment. It's a metamorphic rock. It starts as a sediment, but then it gets transformed into solid state. So I think we should just acknowledge that, that ice cores really are studies of metamorphic rocks. Well, as I mentioned earlier, it all really began with this paper here, published by the Geological Society of London, Phil England and Steve Richardson, actually building on an idea of Ron Oxborough's. At this point in time, if you remember, we had thermal models for subducting plates, but these were all steady state models, and the true insight here was that a thrusting event would be essentially instantaneous from the point of view of the thermal structure of the crust. So what Oxford and Turcotte did originally, and then Phil England and Steve Richardson expanded on, was to say, well, what would happen if we had an overthrust terrain, we thickened the crust, and had a perturbed geotherm, and then allowed that to decay. And what they said was that, well, this will result in a pressure temperature path that will follow some kind of a clockwise loop. Now, previously, starting with George Barrow, in fact, what we considered to be a metamorphic field gradient was this line here numbered in tens of millions of years. And the entire science was focused on what does that metamorphic geotherm mean? It was believed to be something in the crust at the time the rocks were recrystallized. But what England and Richardson essentially said was, no, that's not it at all. The metamorphic geotherm is simply one point on a PT path, which could be as much as right angles to that geotherm. So this launched a whole new study in trying to decipher what the pressure temperature path of a rock was, because the tectonic information, of course, is locked up in what this PT path looks like. So that's where it all started, and I remember seeing this paper a couple of years after it was published, and it just, and as I say, it changed everything. We started, myself and colleagues and others started looking for ways to decipher PT paths from rocks. And at the time I was working in the towered window, which is actually where Oxford and Turcotte originally proposed their model. I had a graduate student, Jane Silverstone, and they're beautiful schists there. And I know this is going to sound a little bit hard to believe, but I was actually hiking up the side of one of these mountains, wondering how we could get pressure temperature paths out of the chemical zoning that we saw in garnets. And as hard as it may be to believe, I actually figured it out somewhere up in the trail in the southern tower window. Here's a beautiful garnet schist. There's a thin section. What we do is we do chemical analyses across these schists, and then here's a chemical zoning profile of that garnet. You see the crossular, calcium and iron and manganese and so on are all chemically zoned. And the idea is that this zoning was created as the rock followed the path, and it was created by the changes in temperature, pressure, and the reactions that were going on in the rock to produce the garnet. And then we put it through the thermodynamic equations, and this is simply a total differential of the pressure and temperature. The trick was to figure out how to get these partial differentials. And I certainly won't bore you with those details. But when we can measure the zoning and we can plug it into this type of equation, and lo and behold, we got out the very first pressure temperature paths from zone garnets. And of course, we were ecstatic when we found that they fit the England and Richardson model almost too perfectly to believe. These are essentially at right angles to the metamorphic field gradient in the area. And we were, as I say, we were quite ecstatic that we thought we really had something important here. And so for the next 25 years or so, this is what I did. we looked at garnets, did a lot of chemical zoning in them, mostly major element works. We also used the garnet biotite thermometer to nail this into absolute pressure temperature space. And a lot of this work, we got to summarize, at least the work we did in New England, I summarized in a fairly recent paper. I've worked in New England for many, many years. It's very nice to work in your own backyard. It's a very comfortable place to work, but the rocks are spectacular. They have analogs in other places in the world. But if we can show you a cross-section across that red line there, which is right across through the middle of central New England, New Hampshire, and Vermont, if you know the area. And this is what we came up with. And it's the culmination of, as I say, 20 years worth of work. We put it all together in a fairly recent paper. And this area is characterized by a number of naps and gneiss domes. You can see the naps and the gneiss domes here in this cross-section. And what we discovered was that each one of these structural units had its own distinct pressure temperature history. And that was what we were hoping for, I have to say. But it turned out to work better than we could have even imagined, because what we were able to do was to not only differentiate different tectonic units, different naps, if you will, but you could turn this over and you could go to an area, and if you could work out the PT path, you could say something about its structural evolution. Because it sometimes in the field can be very difficult to distinguish one stratigraphic unit from another, especially when they're at the kyanite grade. But the thermal structure, the thermal history doesn't really lie. It can't. It has to obey the physics. So if you can determine that there are different pressure temperature paths in different structural units, you can basically prove that there has to be a late or post-metamorphic fault between them. So you can map out structural domains this way. So this is where we were back in the 2007. I was still working in Vermont. It's a lovely place to work, and moving a little bit to the north. But now we're doing some different things. And specifically, we're looking at new ways, new methods, new techniques to try and pull this kind of information out of rocks. And one of the things we're doing is we're using trace elements and the amount of trace elements and the chemical zoning of trace elements in sometimes common minerals and sometimes accessory minerals. But these turn out to be wonderful monitors of the pressure temperature history that rocks have seen. I'll talk a little bit about titanium and quartz. I'll actually start with yttrium and garnet. Yttrium is one of those elements that, well, it's been in garnets for hundreds of millions of years. Its significance. The key thing here, this is a paper about 10 years ago. We discovered that if you have the mineral xenotime present, which is a yttrium phosphate, the amount of yttrium in garnet, here's ppm yttrium in garnet, was an extraordinarily strong function of temperature. In fact, it was such a strong function of temperature that with a typical analytical uncertainty, we could tell the temperature at which the garnet crystallized to around plus or minus 5 degrees. Previously, we were only able to do 25 to 30 degrees with things like garnet biotite thermometer. So we had a factor of 5 better in our precision to determine the temperature of crystallization. Well, if that's all there was to it, it probably wouldn't be too exciting because, who really cares whether the garnet crystallized at 510 plus or minus 5 or 510 plus or minus 25. But this is why I think this kind of work is actually going to open up some really interesting doors. These are both X-ray maps of garnets from this area in central New England showing the distribution of yttrium. And the higher order colors are more yttrium and the bluer, greener colors are lower yttrium. And normally, if you saw from the previous diagram, that when the temperature goes up, the yttrium concentration should go down. But what you see in the inner core here is that the yttrium concentration is lowest in the very center, and then it goes up. And here again, it goes up. And we've seen this in a number of these garnets where xenotime is present when the garnet begins to grow. So one possibility is that the temperature is going down, but if the temperature were going down, garnet couldn't grow. So there's got to be another explanation. And the explanation is when we look at these in pressure temperature space, what we find is that these isopleths are slightly sloped. So we can get this kind of zoning if we have nearly isothermal loading, pressure increases. Now this is quite interesting because the original thermal models of England and Richmond and so on used what they called instantaneous thrusting. Basically, the thrust was just in place and that's what happened. Of course, we all know that can't happen. Thrusts aren't in place instantaneously. So the question becomes, how rapidly do you have to in place a thrust in order to get pressure temperature paths which have this kind of nearly isothermal loading path? And the answer is, we've done thermal modeling various different times to try and get at this answer. The answer is you have to have loading rates in excess of 8 centimeters a year. So this is on the fast side of plate tectonic velocities. It's not completely unrealistic, but what it's saying is that the loading that's taking place in these collisional orogenic belts is taking place at the high side of plate tectonic velocities. Well, that's one bit of evidence. So what we're doing now is we're moving away from simply getting the pressure-temperature path and looking at, now we're starting to look at the rates at which these tectonic processes take place. And what we're working on most recently are some diffusion studies. Diffusion, as you know, is thermally activated. It's a time-dependent phenomenon. And we found that we could look at the diffusion of both titanium and quartz using this titanium thermometer, and also manganese and garnet, one of our old favorites, and we were able to get some additional information about the rates of tectonic processes in this area. I'll show you first some results from the titanium and the quartz, which I think are quite exciting. This is a typical kyanite garnet. Just for those of you who look at thin sections, I think this will look pretty familiar with some biotites on. I want to focus in this white square here. The next image is going to be a cathodoluminescence image of this. About that earlier today. Cathodoluminescence, the quartz all shows up gray, the garnet shows up black, quartz is gray, plagioclase is white, the biotite is black. But I want to focus in on this part in the center of the garnet here. 500 microns across this. These are not big things, 100 microns, about a 50 micron grain here. You can see that these are all quartz inclusions inside the garnet. You can see that the centers of these are all dark, and then they get brighter toward the rim. Well, this puzzled us originally because we couldn't come up with any simple reaction mechanism to have these quartzes zoned like this. They don't look like this when they're sitting out in the matrix of the rock. But what we finally concluded was that this is a diffusion profile, that the garnet grew around the quartz. The garnet has considerably more titanium, so after the garnet is formed, the titanium begins to diffuse into the quartz, setting up this zoning profile. Well, if it is a diffusion profile, then we can model it. And here's what one of these things looks like in detail. In fact, there's a very strong linear correlation between titanium and cathodoluminescence, so we're actually able to model the cathodoluminescence profiles, which are very easy to get, highly sensitive, and highly spatially resolved. Anyway, this is what one of these profiles looks like on the right. If we go from the quartz over here to the garnet, it goes up and then comes back down. And I won't bore you with the details of the diffusion modeling. It's one of those things that you basically turn the crank over and over again until you get something to work. And it works quite well. You can see here's this profile. The red line is our model fits about as well as one could hope. There is an uncertainty here, and the uncertainty is in the maximum temperature. Diffusion is thermally activated, so that depends on what the maximum temperature is in terms of the time scale that you're going to get, and they're basically proportional to one another. So I've done calculations with three different maximum temperatures. They all have the same shapes. All of these are the temperature time histories, but time scales. If the maximum temperature is only 550, then this whole heating process, this whole process which formed the diffusion profile in the garnet, took place in 1.2 million years. The maximum temperature is 600 degrees. It takes place in 300,000 years. My best estimate of the peak temperature is about 580 or 590 or so. So somewhere around half a million years is our best estimate of the time it took to form this diffusion profile. Now, that's not just the time that this thing was sitting there and other things were happening. That's the time to take this thing and grow the garnet, heat it up to the maximum temperature, and then cool it off. So what we're talking about is the time scale for the entire metamorphic heating event. Of course, it's quite a bit shorter than what we used to think about metamorphic heating events, which were on the order of tens of millions of years. Well, if this were the only data we had, I might be a little bit less emphatic about my beliefs that it has something to it. But we also found that we could look at the diffusion zoning of manganese and garnet, and we got a very similar answer. another schist from the same area, the garnet storolite kyanite schist. And if you're a petrologist and look at these things all day in the microscope, you can see that there's a little rim around this garnet here where it's been eaten away. Well, what that does when it eats away the garnet is there's nowhere for the manganese to go, so the manganese piles back up and goes back into the garnet. Here's the manganese zoning map. Here's the manganese piling up at the rim of the garnet right over here. And we can do a profile across there, look at the decrease of manganese going from the rim of the garnet into the garnet. And we know the diffusivity of manganese and garnet to some extent. So again, we can do a diffusion model of this. And when we do, we get very good fits. Now here there's an uncertainty not only in the peak metamorphic temperature, but also in the actual value of the diffusion coefficient. The way these things are measured is that they're experiments done at very high temperature and extrapolated down. So I did a rough error analysis. Oops, sorry. Let's go back to this one. If we use the standard value, what the data suggests, and project that down to the temperatures, we get this total heating event that caused the manganese zoning to take place in 2.5 million years. On the other hand, within analytical uncertainty of the measurements, in other words, if we use the fastest values of the diffusion coefficients, it takes place in 250,000 years, which for all intents and purposes is exactly the same answer that the quartz gave us. So we have two totally independent methods that are essentially within error saying that this metamorphic cycle took place in a few 100,000, maybe 500,000 years, which is, to me, quite shocking, actually, to be honest. Okay, so what we're saying is that we have a pressure-temperature path, and this part of it here went very, very fast, which is quite a bit different from the original thermal models. And the question is, how do we get this? Some of you may have read a paper, a fairly recent paper about the Dalradian, where J. Agnew and Ethan Baxter actually came up with a very similar result by a totally independent method. It was a diffusion study, a totally different method, and concluded that the Dalradian went through a very similarly short heating cycle, which they attributed to plutons that you don't really see, but there are some large gabbroic rocks in the area that they said were the cause. You can't do that here because the PT paths are not those that you would get with plutons. We have nearly isothermal loading, which the yttrium tells us about, so we have to come up with another kind of mechanism. So what I've been trying to do is to find a way to do this with normal collisional tectonics and structural evolution as we might know it. So we're running thermal models. This is sort of a mock-up of a two-dimensional thermal model we're working on. These are red squares, there are rocks we're following, but we're looking south here in Vermont. There's a thick sequence of slurred ammonium sediments, and there's a basement involving Grenville and tectonic slices and so on. And what we're going to do is we're going to look at what happens as we ramp up a thrust and see what the thermal consequences of. So the models are very, very simple in some ways. We simply begin to subduct these things at some rate or another, and so these follow more or less a steady state geotherm. Then we have to do something really rapid. And so the next stage of this is to have rapid overthrusting. And again, this was done at rates of 10 centimeters a year. This is a phase for other reasons I don't have time to go into, but it also is a stage which produces large-scale recumbent folding, the NAP stage. But this will heat the rocks fast enough, but it's not sufficient. So we have to do something else to cool them down equally quickly. And what we are working on now is a model which basically involves mid-crustal extrusion. This whole block here gets extruded outward as the top slides off. There's evidence of extensional tectonics going on in this area, but even as this area is being extruded relative to the blocks on either side of it. And if we do this at rates, again, of 10 centimeters a year or faster, we can get the thermal history that we seem to see in the rocks themselves. So these are the calculated paths we get. You can see the PT paths look similar to what we surmised from the rocks. And the temperature time histories, we have a period of slow heating, and then of course this could go on for tens of millions of years as we could bury these rocks as slowly as we want to. But then there's a very rapid event that takes place in, well, in this case, in around 500,000 years or so of heating and then cooling, and it fits, at least as well as we can tell, it fits the results from the diffusion modeling quite well. So this is what we're working on now. We've moved away from looking at PT paths and tectonics to try to get at the rates of these processes. And the rather surprising result, as I mentioned earlier on, is that these rates seem to be significantly faster than certainly I would have ever suspected. And I think most of my colleagues would have suspected. But it does raise some interesting implications. I mean, we're talking about timescales here, this green area, this path here, being on the order of 500,000 years. That's the same time scale as the ice core that we were just hearing about. The implications of this for climate evolution, the implications of this for species evolution. It's hard to imagine doing something like this without creating a mountain range, for example, which would have all kinds of global impacts. I'm going to leave it here, but simply say there are other bits of information which suggest this. There's geochronology which suggests this. And I think that we'll see in the next few years that perhaps, well, I hope we're going to see some refining of this, but we're perhaps going to understand a little bit better exactly how it works and the implications.